Looking at related rates is a nice application of derivatives. When you have a formula, let's say it's a function of just one variable x, you might write the equation as y equals some relation of x, right? And so you have that relationship between y and x. But a common thing is for those variables to be related, say, to another variable, like time. So time is probably the most common use of this. So y might be a function of time and x might be a function of time. And now you have an equation y that depends on x, but can derive another equation that is dy dt related to dx dt. So in related rates problems, that's essentially what we're going to be doing. We're going to start with some initial equation and then turn it into a relationship between the rates of change of those two variables. So I want to look at two different examples to illustrate this topic of related rates. The first one here is inflating a balloon. When you inflate a balloon, you're adding air, so you're adding volume. The volume is increasing. As the volume is increasing, obviously the radius increases too. So this is a related rates problem. The rate at which the volume changes is related to the rate at which the radius changes. If we start with the formula for how volume is related to radius, we can then figure out how the rates of those changes are related as well. And so that's what we're going to do next. Let's take a look at this related rates problem. We have air being added into a balloon. As the air is added in, two things are changing at once. The radius is increasing and the volume is increasing, and obviously those two things are interrelated through the equation for the volume. So let me add a little text cell here. We can write that in just so we have the notation on our screen. The volume of a balloon, which we can approximate as a sphere, is going to be 4/3 times pi times the radius cubed, right? So this is our expression for the volume of a sphere. Then if we want to know how these rates are related, we can differentiate this equation with respect to time. Volume is a function of time, radius is a function of time. So taking the derivative of this whole equation with respect to time will tell us how volume and radius are interrelated. So on the left-hand side, we'll get dv dt. And then on the right-hand side, we'll get, well, it's radius cubed, so it's differentiating a power law. What's in front, the 4/3 pi, that's just constant. So we'll bring down the 3. So instead of 4/3, it'll just be 4. The pi will remain the same, so we'll leave that pi. And then we subtract 1 from the power, so it becomes r squared. So this is essentially our volume. Oh, wait, forgot one thing. So it's the chain rule. We have to apply the chain rule because radius is a function of time. So we're taking the derivative with respect to time. So we first take the derivative of r with the derivative of this function with respect to r, and now we have to take dr dt. So then we have a dr dt at the end. Okay, so let me just close this here. And we have those on the screen. Okay, so 4/3 pi r cubed, and then dv dt is going to be 4 pi r squared dr dt. Now, if you're familiar with formulas from geometry, 4 pi r squared is the surface area of the sphere. So the rate at which the volume changes is the surface area times the radius rate of change. Okay. So we have a specific problem. Air is added when its radius is 10 centimeters. As the air is blown in, the radius increases at a rate of 1 centimeter. And we want to know at what rate is the volume increasing. So we want to solve for the rate at which the volume is increasing. That's this, using this expression over here. So let's create a little function for this. So define a function, and this is the volume rate of change. You might notice in here that it's sort of predicted a little bit what we want to do. We can call it dv dt. as a function of r. That's certainly reasonable. So let me tab forward here. So we'll call our function dv dt. That's the volume rate of change. And it's a function of the radius, but it's left out something. It's left out that it's also dependent on the rate of change of the radius. So we have 4 times 3.14, so it's interpreted pi. But we really have two variables in here. We have the radius and we have the rate of change of the radius. So I'm going to add a second variable here, and let's call that one dr dt. And then I need to add into my formula at the end times dr dt. Okay, so dr dt is my rate of change of the volume. Rate of change of the radius. Okay, so while that's running, we have a function that depends on those two factors. Those happen to be the values that I have in here. So let's just use this new function, dv dt, and then we're going to apply a value of r equals 10 and dr dt equals 1. Okay, and so now we find that our radius is changing, our volume is changing at a rate of 1,256, and the units would be cubic centimeters per second. So 1,256 cubic centimeters per second. Did it do the math right? We can check this quickly. So we're going to do 10 centimeters squared, so that's 100, times 1, so it's 100, times 3, which is about 300, times 4, which is about 1,200, so it looks like the math worked out correctly in this case. All right, so having seen one related rates problem, let's think about how you solve these problems in general. So this is the problem-solving strategy from the textbook. The first step, for me, I would say I always draw a picture of things. That's very helpful to me. You don't have to draw a figure if that's not helpful to you, but I find that it generally is for me to have a picture of the situation and then assigning variables to any of the symbols that are in the problem. So if you're looking to determine what are the related rates, it's the related rates of what. So you need to identify what you're relating. Then you need to look at the relationship between them. And so numbers 2 and 3 here are identifying the variables or sort of quantifying the variables that you need to relate, and then putting it down an equation that relates those variables. So in the balloon example, it was the volume is 4/3 pi r cubed. Okay, so you know what the variables are. You've drawn your picture. You've got a picture of a balloon. You've got the radius. Then you've got like the volume indicated somewhere. Volume is one rate you're going to determine. Radius is the other, and they're related by this equation. Volume equals 4/3 pi r cubed. Then you differentiate that equation. So you sort of use implicit differentiation in general. You might have an equation that's exactly solved, like v equals in that case here, so you can just take the derivative of the equation. But in general, you're just differentiating the whole equation, whatever form it's in, which means using implicit differentiation in general, and then applying the chain rule, because you're taking the derivative with respect to something like time, some one additional variable in the problem, volume, radius, and now introducing time to find rate of change. So that's what we're calling the independent variable here. So independent variable, in our case, the previous example would be time. And then the result of that, once you've done the differentiation, you'll have a relationship between the two derivatives with respect to that independent variable. In other words, a relationship between the rates of change. So if you know particular values, at that point you can plug them in and solve for whatever the unknown is. So any related rate problem, you will approach in that general same way. So draw a picture, figure out the variables you need, write down an equation, and then differentiate that equation and plug in. All right, the second example I want to look at is a rocket launch. We have a rocket that is some distance, horizontal distance, we're calling x, away from you, and then its vertical height as it's rising will be called y. And we're supposing that we're filming this, so we're taking video of this from some distance x, and then the angle at which you're viewing the rocket will change as the height changes. So in the diagram we have here, this is how far the camera is away horizontally from where the rocket is launched, and then its launch, it results in a height y sometime later, and the angle here will relate to the height here. Right, x is going to be a constant. We're assuming it's going straight up, so this is not changing, but both the angle theta and the height y will be functions of time. So we have a right triangle, and if you recognize the SOHCAHTOA applies here, you can say tangent of this angle is opposite over adjacent. So tan theta is y over x. So this is our relationship between these three variables. So following the steps in our process, we've got our picture, we've got the variables located, and we've got an equation relating those variables. Now we can differentiate it with respect to the independent variable. And in this case, again, it's time, right? The rate we're talking about is the rate at which these variables are changing over time. So we're taking d by dt of this whole equation. Now on the left, that results in the secant squared. So derivative of tangent is the secant squared, but remember it's chain rule. We're taking d by dt. So you take the derivative of this outside function, tangent, which is secant squared, and then you multiply by the derivative of what's on the inside, d theta dt. Now on the right-hand side, we have y over x, and x is just a constant. So you don't need to differentiate the constant, or when you differentiate a constant, you just get 0. So all we really need to do is take the derivative of y, and then the 1 over x part will just remain. So we still have a 1 over x, and then we have dy dt. So now we have our relationship between these two variables, and if we have values for how far this is away, and then at a particular angle, and one of these rates, we can figure out the other rate of change. All right, so let's look at the example as written here. Suppose you're 100 meters away from a rocket launch. The rocket rises at a steady rate of 70 meters per second. When the rocket is 200 meters high, how fast is the angle of view changing? So now we have the relationship between the angle, the height of the rocket, and the horizontal distance. And we use that to find the related rates, right? We have a relationship between the angle rate of change and the height rate of change. And then we still have in this formula the horizontal distance and the angle go in there as well. So what we're looking for is how fast the angle of view is changing. So we're looking for this part. So we'll solve for this ultimately. But we're going to need to plug in the angle, and we don't have that given to us in the problem, so there is a step we have to do first. There's sort of a part A before this as part B. So part A is to find this angle. What we do know is the rocket is 200 meters high, and you are 100 meters away horizontally. So the first equation, the tangent theta equation, is that we can solve for theta so that it's arctangent of y over x, and so y over x is 200 over 100. Important to remember when you use your calculator, or if you're Googling the calculation or whatever you're using, most often the default for trig functions is to report angles and have angles as input in radians. So when we do this, like if you type this into Google arctangent 200 over 100, it would most likely give you the answer in radians, and that should be 1.107. You can always convert it to degrees if you want to think about the value in degrees, and that would be 63.4. But just always be cautious of that when you're working with trig functions. The answer that your calculator spits out, unless you've set it to degrees mode, will probably be in radians. Then we can use the second equation, so the rate of change of the angle. We're going to plug in everything we know, so the rate of rise of the rocket is 70 meters per second, so that's the 70. And then we have the x is 100, and we're going to divide by the secant squared of this angle that we found. Now again, because we have the trig functions here, we're finding angle rate of change, the way that this is going to come out is going to be in radians per second. So you could take this answer, 0.14 radians per second, and if you'd like, put it into degrees and get 8.03 degrees per second. All right, so that's how you solve these related rate problems. We have a word problem here with some values. You might need to use the equation that relates those variables, and then you might need to use the related rates equation to solve them.